Welcome to the University of Kiel. My name is Stanislav Gorb and I am leader of the group of functional morphology and biomechanics at this university. We are a group of mainly biologists interested in nanotechnology. So we study different biological surfaces, starting with the gecko feet, insect feet, snake skin, plant surfaces, in order to understand contact mechanics phenomena such as adhesion and friction in these systems, and with the idea to implement the same phenomena into technology. So what we do is by using microscopy techniques and different kind of force measurements to try to understand principles behind such biological systems and then try to implement the principles. Today I will present you three different topics from our ongoing research. The first topic is so-called gecko tape. With a collaboration with a real company from southern Germany, we designed a product which can adhere to different kind of surfaces without using any kind of glue. Adhesion without using glue is one of the oldest projects in my group. Why it is so exciting? Imagine geckos, they use only dry structures, dry surfaces, in order to adhere at a ceiling, and very fast, in a dynamic way, and without leaving any residues on the surface. Of course, it is a dream for the technology. So we spent many years in studying not only geckos, but also studying insects, spiders, all other animals which can master the same ceiling situation. And we find out that all this system, they have one in common. They have very little hairs with very specific tips. And those tips, they look like a little band. They are very thin, very flexible, and can be easily adaptable to any kind of surface roughness. We worked many years together with a company which was able to implement this knowledge in a real product, which is called gecko tape. You see this gecko tape on this glass slide. In fact, it is nothing else as just piece of microstructured polymer, and this microstructured polymer contains little outgrowths which are terminated by a kind of mushroom-shaped tip. And this mushroom-shaped tip is able to adapt to any surface profile. And another interesting feature of such a geometry is that the tip is able to prevent crack propagation. We did a very detailed study in a microscope in order to show what's going on during the contact formation and breakage, and find out that the contact or the breakage is formed, the crack is formed in the middle of every single mushroom-like structure, and the crack is propagating from the middle to the outside. And in fact, this is a kind of self-stabilization system at the level of every single microstructure. And you can imagine if you have millions of such structures on the surface, they can do even more together. They stabilize the entire contact. So you see that the material is not sticky at all actually if I put my finger on it, but if I take flat surface like a piece of glass or any kind, we can take Teflon or any kind of surface, bring it to the contact and you feel adhesion. You can even hear it. So this is a real magic, adhesion without glue. In fact, we use pretty soft polymers for designing these kind of gecko tapes, but these gecko tapes have some problems on the very rough surfaces. And geckos actually don't have any problems on any kind of roughness almost. So the question is, what is specific about the gecko structure which can master adhesion on roughnesses? And the answer lies in a very fine substructures in the nanometer range, and that's why we decided to try to use carbon nanotubes in order to mimic these fine structures.
Hello, my name is Clemens Schaber and I am a postdoc here in the Department of Functional Morphology and Biomechanics. I will show you the force tester Basalt 01, with which we can measure forces of adhesion and the Young's modulus of many different materials. to do so, I need to insert a calibrated metal spring into the device. And there is a small sapphire sphere glued to the spring. And the deformation of the spring is measured with these fiber optical sensors. Here we measure the mechanical properties of vertically aligned carbon nanotube arrays. And these carbon nanotube arrays are fabricated by the group of Professor Schneider at the Technical University Darmstadt. Our specialty here is the measurement of forces between the microscopic and the macroscopic scale.
By using this knowledge, we decided to start a new project on the frog tongue. Frog tongue is the topic of my postdoc Thomas Kleinteich, who is very excited about the ability of frogs to adhere to different kind of roughnesses and to different kind of surface chemistry in a very fast and dynamical way. And right now, this is a kind of ongoing research in the group. He's trying to measure the movement using high-speed cameras and to measure forces which frogs can achieve on different surfaces. So this is a kind of follow-up project where we try to understand systems which also use, in addition, kind of glue. In this case, this is the mucus. This is the fluid on the tongue on the frogs.
Okay. Hello, I'm Thomas Kleinteich. I'm working here as a postdoc, and I'm interested in the adhesion of frog tongues. And what's special about frog tongues is that it's a wet adhesive system, not like gecko or beetle feet. It's also special because the adhesion happens really fast, in a time frame of a few milliseconds, and it acts on a variety of different surfaces. So frogs can feed on bird, mice, insects, and so on. And it's a wet adhesive system because there's mucus involved, so it's not like gecko adhesion or beetle adhesion. And I'm using this micro CT scanner to study the anatomy, the morphology of frog tongues. It has an X-ray source here, and there's a camera in here which is sensitive for X-ray radiation, the detector, and the sample is in between. It is mounted with a needle in this plastic tube, and this tube is filled with ethanol. And so the sample will rotate inside the X-ray beam, which is different to a medical CT scanner. In a medical CT scanner, of course, the sample won't rotate in the medical CT scanner. The X-ray source and the X-ray detector rotate around the sample, in which case would be a human. And the advantage of having a rotating sample with these desktop CT scanners is that we can move the sample really close to the X-ray source and get a very high spatial resolution, which is in the range of less than a micrometer. And so we can study surface structures and the cross morphology with the same machine. Now I'm starting. So now first I close the specimen chamber of the CT scanner. And so I get a three-dimensional computer model. And of course I can rotate it, have a look at it in all three dimensions, and I can have sections through the sample and see the complex arrangement of the muscle fibers inside the frog tongue. And also with this micro CT scanner, because it has such a high resolution, I can study the surface profile of the frog tongues. So I can even zoom in to see the taste buds and the papillae on the surface of the frog tongue. Okay, so we can show that frog tongues have a really complex three-dimensional arrangement of muscle fibers as well as of surface structures and mucus glands. And the next steps will be to reveal the physical and chemical properties of the tongue itself as well as of the mucus which is covering the tongue.
Biological contact phenomena is ongoing research topic not only in Germany but actually worldwide. Many groups are trying to develop, based on the knowledge from biology, technological system. So contact phenomena is a very important topic. And we are very much convinced about the concept of Beilstein and Beilstein journals. That's why we planned special issue on biological adhesion and bio-inspired adhesion, and we hope this special issue will find broad audience worldwide.